Hello people, everybody, welcome back. Okay, so this is going to be the compilation of the last series I just uploaded. It could have been uploaded as one thing, and so this is that. I just wanted it to be all in one place. So maybe if you like, it can be used as a reference or something, or people can watch it back and hopefully learn something new. I don't know. Also, sorry, my eye is really itchy right now, so I feel like I look insane. But this is just a quick introduction situation for that. I thank you for all of the support this past week or so on the new videos and the Ted Kaczynski video. I know I have a lot of new fans from the Ted Kaczynski video. I'm seeing you, I'm hearing you. I'm going to do some more fun stuff like that soon. This video is fun too, but it's a little more math heavy than my Ted Kaczynski video, probably. You don't have to pay attention to every single thing I'm saying. You can still kind of follow along. I don't know. I'll be making jokes throughout, and then my next uploads, I'm turning towards something funnier for a minute. But all of the Ted Kaczynski fans, all the math fans, all the comedy fans, I'm hearing you, I'm listening, and yeah, I'm gonna do something for you soon. So thank you for all the support. Please remember to like and subscribe. I really appreciate all the kind words and stuff lately, you guys. You guys are nice guys. Other than that, hope you enjoy this video. I hope it's accessible enough for people, and hopefully it's just enjoyable content. I don't know. Whatever. Alright, so thank you for watching. Remember to like and subscribe, and I will see you tomorrow probably. Or later today. We might see each other. You might have already seen me today. I'm not sure what I'm doing yet, but I've got a couple of videos coming out rapidly here, so stay tuned. Thanks. Love y'all. Bye.
This ain't what you want. Project. This ain't what you want. This ain't what you want.
Hello, people. Everybody. Welcome back. Okay, so today what we're doing is we're doing a math video today, everybody. That's what it is. We're doing a math video. So, I don't know. If you know me well, you may know that I know a whole lot about math. I do, it's true. I've been told for longer than I've had a YouTube channel that I should make math videos. I've been always hesitant because I understand that I know this stuff well, right? And I don't know how to explain it all the time, right? This is a personal opinion of mine, but math teaching is very... Can we calm these cars down? I think that math teaching is very important. My dad was a math teacher. Math teaching makes or breaks somebody's liking for math. That's what I'm getting at. I don't know. I guess I've been nervous to breach this. I don't love my new haircut. It's a little short, but I got it for graduation just so I could all look like, I look like a non-gender alien walking up there. I'll put a picture of it on screen. But I don't know how accessible it is. I don't know how entertaining it is. I don't know what I need to explain. I don't know if it's going to be lost on everybody. But listen, today we're going to take a crack at it. So the background here is I took a 400 level linear algebra class. I am a math major, and the grade was broken up into the homeworks, the exams, and then a project, right? And so, we were supposed to pick a project, and I didn't really pick a project. He was pick something on this list, and I was I don't really care about any of the things on this list. I wrote him something, but I didn't really I didn't even submit a project proposal. It was how does this relate to computer science? And I don't care. You know what I mean? I like math for math. It's just fun because it's fun. You got to do it for the love of the game. Okay, quantum computing is cool, but I didn't ask about quantum computing. I asked about linear algebra. I asked about math, okay? So you know what I'm saying? Stochastic matrices, those are kind of fun. But anyway, we're getting off topic. So I was, I didn't even have a topic proposal because I was I don't know. And then he showed tensor products on screen. And I knew exactly what I wanted to do. So today we're going to talk about tensor products and a very specific type of tensor products. Or if other people who know these things want to help out with this, it might be kind of a fun community project or whatever. But I found a very special type of tensor. I don't really know what the implications of it are. I just know that this is it's a fun little thing you can do. So with that, I guess we'll get started, huh? So let's see here. We really need to get our ducks in a row. I should start with this simpler example before I talk about what we're talking about today, which is, this is what's going on. There's algebra, and there's linear algebra. So algebra, which is 3x plus 1 equals 4. Okay, and then x equals 1 would make that statement true. 3 times 1 plus 1 equals 4. True. Okay, so that's algebra. Now, there's linear algebra, which is a system of equations. So it's like, okay. And then it's a little bit more work, but you would see that, like, what would it be? X equals 1, y equals 2. And then you plug these numbers in, and these are true statements, and then yay. And then yay, you can see that a true fact is true. So that's algebra, you know, and that's linear algebra. And then so, like, the difference in linear algebra is instead of one equation, you're doing a system of equations. Then another way to write this now is a matrix. So look, we have 3x plus y, 1x plus 2y. So you could write just 3, 1, 1, 2. And then you could write it like x, y. So I'm showing you this to talk about, this is how you would multiply this out. Top number goes with the first column. The second number goes with the second column. Like that. And then we said that equals 5 and 5, which we would write as 5 and 5. So, okay, like, I'll put timestamps up because if you know what's happening, then, like, we can cut to it. So this is how, like, well, actually, no, I'm doing fine. Just, how about you guys let me keep going? Let me talk, okay? You know what I'm saying? Is that all making sense to you? So what I've just explained to you is called matrix multiplication. So, and that's like a matrix in a vector. So these are vectors. This xy is a vector, 5, 5 is a vector. And then they're not equal. Because they're next to each other, they're not equal. Those are two vectors. So then you'd get like, we're getting like ax equals, say, y. Okay. And then, so that's like a fun little equation. All right. So that's how you do that, whatever. And then, and then you have matrix, and then you can multiply a matrix by a matrix. So you can go like A times B equals like, and then you'd have like 1, 2, 3, 4, and then say X, Y, Z. Okay. And then the way you multiply matrices like this row times this column, okay, is going to give you, you're going to get a new matrix from this. So a matrix times a vector equals a vector, but a matrix times a matrix equals a matrix. It's like how an even number times an odd number is still an even number. No, that's not the same at all. Don't worry about it. But a matrix times a matrix still gives you a matrix. All right, so this multiplication that we're talking about right now is going to give you this entry. It's a 2 by 2 matrix. These are 2 by 2s. So see how it's like there are 4 entries. See how that equals 4. But there are 2 rows and there are 2 columns. 2 columns. See, and then you multiply the rows by columns and you get 4. It's very archaic, but it's nice if you think about it. But so that's kind of what's going on there. We got the rows, we got the columns. It's just 2 by 2. So 2 by 2 is gonna, this is gonna give us a 4 by 4. So let's finish this off here. Actually, we don't have room, so let's redo this A times B here. So this is gonna be like W plus 2y, and then X plus 2z, and then we have 3W plus 4y, 3x plus 4z, if that makes sense. So basically, you have this and that equal this. You have this and this equaling this. Okay, and then we've got this and this equaling that. That and that equaling that. Is that like 3D? I kind of killed it with the colors there, did I not? That's fun. Cool. Well, okay, so we understand matrix multiplication. Oh, this is going to get complicated, everybody. Okay. All right. So I had to do a project. You know, we had to pick a topic. I didn't have a topic. This is what I ended up talking about because I don't know. My teacher actually said, don't look into this. I'm not kidding. My teacher was like, don't look into this. And I was like, well, I'm doing it anyway. And I got 100% on the project and the presentation. I presented this for people. They liked it. Okay. And now I'm bringing it to you guys. So That's a matrix product. Now we have something to talk about called tensors and tensor products. This is where it gets fun. If you were bored so far, this is where it gets fun. Don't you worry. So, tensor products. All right, so this is where the real magic starts. Let me look up a basic tensor product because we're gonna do some pretty complicated tensor products, and honestly, the more simple ones don't really even matter. But I just want to show you like kind of where the motivation for this came from, I guess. Okay, I remember. I think that you guys thought that I forgot what I was talking about. Let's get a smaller can we get a smaller pen? You know, like we have a lot of writing there's a lot of ground to cover. Hello? Okay. On a closing note here, I guess, we'll note that the 2x2 matrix is a row times column situation. And this kind of color coordination, this row by column product thing is something of note. And then just kind of this color coordination. And just know that like what we've talked about is matrix multiplication. And then we'll take it from there. Okay, we're building towards a commutative Kronecker product. All right, that's what we're doing. So, hello people, everybody, welcome back. Welcome. Well, okay, so if you didn't see part 1 of the video, if you're a math person, don't worry about it. If you're not a math person, that's just some kind of fun like stuff up front. You don't really need to see the first part of the video to understand what's going on next. Like, I'm going to try to make each part as accessible as possible on its own. I'm just going to try to keep going with what I was talking about. This was one class presentation, so I'm going to try to like keep it. We're working towards commutative Kronecker products. That's the goal. So, but right now, where we're at is we are going to talk about what tensor products are. So here. So far we've talked about matrix products. And then the roadmap is we're going to talk about tensor products. And then we're going to talk about Kronecker product. Okay, and then we want a specific type called a commutative Kronecker product, which it means that so if we call that the Kronecker product symbol, call this the Kronecker product symbol, and B is going to equal BA. Okay, like that. So let's start with, so we got matrix products, tensor products, Kronecker products, and then we've got commutative. Let's start with what is a tensor product. That seems easy, right? So let's start off with a normal tensor product. So if usually you take a tensor product A and B, usually these would be vector. We talked about matrices. Okay, so we talked about taking the tensor product of two things. Typically you would be talking first about vectors, and then we have matrices that are written like so that's a matrix, right? And then vector, as we talked about in the first part, is something like x, y. Okay, so when we take tensor products, usually we're taking the tensor product of two vectors. Take the tensor product of A, B, tensor product with C, D. So we do the multiplication differently here, where the first, so the way to think about this is the first of the two vectors is like the shell, A, B. And then the second of the two vectors is kind of like the meat of it. So you see what I'm saying about the meat in the shell? Like the first number is like the outside number, and then the second is like the inside number. So you know what I mean? Does that make sense? So that's how, you know, the concept of tensor product works. And then, you know, with the matrices, remember how we were saying a 2x2 matrix is like 2 rows and then 2 columns, right? So this is a matrix like, you know, XY is a 2x1 matrix. And then if you take the tensor product of two 2x1 matrices, you end up with something where you multiply the first numbers and multiply the second numbers, you end up with a 4x1 product. And so what that looks like, as we said before, you have A, B, tensor product with C, D is equal to A, B, C, D. So this gives us a 4x1 matrix, or a vector rather, because it's 4x1, of AC, AD, BC, BD. that makes sense? You kind of multiply these. See if we can color code it. So you kind of multiply these term by term. If you can see that, gives us that. Okay. So now you can see it's a 4. It becomes a 4 by 1 situation because we've got 1, 2, 3, 4, 1. Okay. So that concludes. I think that concludes our lesson on tensor products. So we talked about, tensor products of something like x and y as vectors, right? So the Kronecker product is a special type of tensor product where, remember how we were talking about matrices? Well, we're back to talking about matrices. The Kronecker product is a tensor product. Let's define this. I would define it as a tensor product. I hate this pen, okay? I hate this. What a disaster. I'm doing my best, folks. All right, it's a tensor product of matrices. So what does that look like? Well, okay, so we're just going to jump into an example. And we're just going to, this is maybe part 3 where I just fucking let it rip, all right? I'm just going to go for it. So what if we want to take the tensor product of matrix A, B, C, D. Oh my gosh, I cannot write D. Tensored with E, F, G, H. Obviously, that would give us, a 4. So notice how, remember how I was saying, that's why I said this before. So notice how this is a 2 by 1 and a 2 by 1. It makes a 4 by 1, right? Now we're doing a 2 by 2 and a 2 by 2. So this is going to give us a 4 by 4. So this is going to give us a 4 by 4. So this matrix should be a 4 by 4, and it is. So now this becomes A, E, A, G. You see how we just kept these A's the same. We kept these A's the same. C is the same. All right, we kept the A's the same. We kept the C's the same. We kept the E and the G in a row. We kept the E next to the G. See how the E and the G are next to each other. Let's undo all that highlighting now. Okay, so that's the first row, or that's the first column. And then we have A, F, we have A, H, C, F, C, H. Then we have B, E, B, F, B, G, D, G, D, H. Okay, so we've got this, and you'll notice, so we have 16 pairs here, okay? And as we said over here, as conjecture, the 4 by 4 does turn into a 16, the 4 by 4 does turn into a 16 entry situation, right? So this is matrix, call this A, B, right? And that's what we get. So now what we want to do is take B, A. And then B again is E, F, G, H. A is A, B, C, D. Okay, so one thing that I am going to try to do here is keep the letters in alphabetical order because it should make things easier to see. So what would that look like? If we take this product, we're going to get a 16 entry 4 by 4 situation. Now we know that we can think of this matrix as boxes. This is the E box, this is the F box, this is the G box, and this is the H box. Because if you look up here, looking at this matrix, you can kind of see that there is an A box, a B box, a C box, and a D box. If you want to pause and take a look at this, how, these are all A's, these are all D's, that matching up. So with this, we're going to have in E, F, G, H, we're going to have these blocks, okay? So we're going to rewrite this as, like I said, we're going to keep the letters in alphabetical order. So A, E, C, E, right? This is B, E, and then this is D, E, right? Now, and then this box is AF and DF. Is this right? Okay, yeah, that's right. Yeah, I'm making sense because this is a little like I know exactly how this turns out, but it is a little bit yeah. As you can see, there's a lot happening here, folks. All right, and then A, B, C, D. Notice how we're keeping, like it's really hard for me to exactly describe what I'm keeping and what I'm like, what is staying the same here. I'm hoping that you're seeing this, that like this gets copied in each box, you know, and then whereas, you know, this is this. When I fill in the rest of the G, 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 H, 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 H. Okay, so why do we do that? Because remember, we want to find when A, B is equal to B, A. Okay, so how would we, like, how would we go about doing this? Because, like, I don't know if this is just how my brain works. Like, I don't know. I guess my math brain is developed to a certain extent where this just is, like, the natural step to me. But it's like, we found this matrix. We found this matrix. We want them to equal each other. So let's set them equal to each other, right? Like, it's like, sometimes it's the simplest things that work. You know what I mean? And not to say this is simple, because it's not, but like, it seems like the dumbest thing, you know what I mean? It's the, the simplest explanation is the right explanation, whatever the hell that is. This is one of those things. You just, how would you find this? Because really, I'm asking for a description of like a very unique type of algebraic space in this, like all this rah yada yada, like, you know what I mean? But at the end of the day, it's just like, well, what happens if we set them equal to each other? And by the way, remember, when I said in part one that I didn't know what the implications of this were, it's because I'm just setting things equal to each other instead of, like, you know. So that's that's also part of the problem. But you do it for the love of the game. You know what I mean? I'm a love of the game actor, and so like that's what brought us here. And I mean, you all are enjoying it if you're seeing this. So I'm gonna get with it because this is where this is actually really where it gets fun. I'm not gonna lie with you. This is where I'm not gonna lie with you. I'm not gonna lie to you. This is where it gets fun. Like, this might actually be its own, like, this might be the real start of, this might be the start of another part, just because this is where the shit gets real. I would just like to say we are now leaving linear algebra, okay? No more linear algebra. It's not going to help, it's not going to be helpful to us. We can't use it anymore, all right? Now, let's go. So we have A, E, A, F. Let's make this bigger. Hopefully that's like legible to everybody. That's the first matrix, and that's A, Kronecker product B. And now we're gonna set it equal to B, Kronecker product A. Fuck. I don't know how long I've been muted. Okay, it's okay, everybody. I realized I muted the mic and I freaked out, but I checked it and it was at a fine time, so don't worry. Continuing. So basically all I did was draw out these matrices. That was all I lost. So I drew out these matrices. And so basically we need these two. We have this product. We have this product A and B, and we have this product B and A, right? And for AB to equal BA, what really needs to be true is all 16 entries in each place must be equal to each other. So instead of two things equaling each other, it's 32 things equaling each other. But don't worry, because we're going to use our problem solving skills and our pattern recognition skills and things of that variety, okay? We're going to come out on top. This is not as big of an issue as you think it is. It seems like a lot, but don't worry about it. All right? I'm going to walk you through it gently. That's what's going to happen. So we got to take it from the top. That's all we can do. All right? Let's get rad involved. Yeah. So this number must equal this number. Because remember, A, B, C, D, E, F, G, they're all numbers. Okay? That's the nice thing. But we don't have to worry about the numbers right now, which is why we're going to recognize a pattern, which is what's cool about math, everybody. So just everybody hold their horses. That's what I say. So those two things would have to be equal to each other. So that means A. All right, let's not. I don't love that color, you know. These are customizable and I still hate them. But anyway, A, E equals A, E. Now, that seems dumb, but that's important, okay? That's kind of a thing. Things that seem stupid like that are going to become more, like, make more of a difference than you would want to believe, okay? Because check out what happens next, okay? So we have this number has to equal this number, okay? So writing that out, that's A F equals B E, okay? And then just when you thought this was getting boring, this does kind of get interesting, because so the next thing we gotta do obviously is make sure this equals this. Okay, writing that out again, we have BE equals AF. But now we run into something interesting, folks, because we've already written, it's already been said that AF equals BE. So now we're saying BE equals AF. Same thing. They're equal to each other. Okay, so this gives us like a hint, but we do have to keep going, but this is going to give us a hint as to what we might be able to do with it. Like, maybe we can simplify this and it's not so purposeless after all. So, because we know that whatever AF is whatever BE is, which is also going to be what all of those entries are going to be. They're all the same, like, they're all equal to each other. It's great. So, continuing. BF equals BF. Well, that's an easy one. That's another one of those. That's actually similar to AE equals AE, right? Okay, so that's actually, you know, this seems really, we have two equations so far. You know what I mean? So, okay, next, AG equals CE. We have AH equals DE. And then we just did this. We just did these pairs, right? But then if we look at this pair next, we will get another CE equals AG. And also because this is normal multiplication, GA equals AG. That's not a given, but I should have said that. So just to clarify, that is true. Like, that is an assumption. But we have a pair of similar equations again, folks. And then if we look at these two, this pair, BGCF, okay, we get another CFBG. So we can simplify that again. And then actually, if you look here, oh man, this is getting messy. AH DE AH DE. So I feel like you can kind of see what's happening here. Like I'm gonna do the rest of this out without commentary, and then I'm gonna come back to you with a kind of simplified situation. But I feel like you can kind of start to sense the pattern here, where you just kind of match things up and you notice that they are repeats of each other, essentially. You just pick up on the repeats, and then so the next step here is literally just to pick up on the repeats and simplify it from 16 equations to hopefully less than 16 equations, right? So I'm going to write that out a little bit, and I'll be back in a second. Also note that this entry, and this entry, and this entry, and this entry all have to be the same. That is the pair DFBH, and they're equal to each other. Okay, so that's all the pairs. Again, here's another one. Here's another one that's the same. That's a pair that's itself. That's a pair that's itself. BH, DF, we talked about this pair. We now simplify this to let's simplify this down to less equations. So we have we have AE equals AE. So we're just going to call AE a fundamental pair. Okay, we'll put it in red. Now also, if we look at this, we've got C, the corners are fundamental pairs. So, you know, we have this matrix, we just take a look at one of the original matrices, okay? The four corners are these fundamental pairs that will always equal themselves, okay? So we're gonna set those aside. And those are AE, BF, CG, and DH, okay? And we wanna so like a video game, the fact that this equals itself is kind of a glitch in the matrix, if you will, because we're working with matrices. But this is kind of a glitch that we're going to like exploit / use to our advantage coming up, is these fundamental pairs. We're going to take advantage of the fact that these always equal themselves. That's going to be helpful to us, all right? In the way, I'm sure there are other ways to go about solving this problem, but in the way that we're solving this problem, we're going to use that to our advantage. So the next thing we'll do is take note of we're just going to now list the rest of the equations. And the fun thing about this is in all of these setting things equal to each other, we have nothing without a duplicate. There's everything has a duplicate somewhere. So this simplifies nicely. So we have these four fundamental pairs, which are, you know, the four corners, and then our other kind of like fundamental equations, if you will, and I may, are AF equals BE, DF equals BH, AG equals CE, DG equals CH, DE equals AH, and BG equals CF. Okay, so the next thing to notice here, that like when I was trying to solve this problem, the next thing I noticed is that we have AE equals AE, okay? And then we have these equations. And if you'll notice, you can't find an equation with an A that does not also have an E on the other side. And like, isn't that why? Like, isn't that weird? Isn't that interesting? Like clearly, like because I don't know what it, like, I'm not being like, but like him and Han or whatever they say. But like, isn't that kind of interesting? Like this isn't set up. This is what I was doing, and I noticed this, where like you can't find any A's without an E. And likewise, like you can't find an F without a B, right? You can't find a C without a G. And then D and H. They're all fundamental pairs. You know what I mean? So the next question is like, what do we do with this? Because this is great, but like, what do you do? As I was working through the problem, my vote was to simplify it. Okay. The next thing I thought about was like, if I can throw a 0 in, if I can set something equal to 0, right? That might eliminate some things and simplify this down even more. All right. So that's what we're going to do next. We're just going to throw a 0 in. Maybe make this another part, Adam? I don't know. And then how do we throw a 0 in? Is we just say that something equals 0. That doesn't seem that hard, right? Let's just call something 0. Let's say C equals 0. Okay. If C equals 0, then C times anything equals 0. Okay. So that would imply that CG equals 0, CE equals 0, CF equals 0, CH equals 0. So now if all of this is true, then C equals 0 means that AG equals 0. So okay, this might be a little hard to follow. If all of this is true, this is a little bit hard to explain, but basically what's happening here is C times G is a fundamental pair, okay? These things are not fundamental pairs, okay? And what you find is that if, for everything to be true, if C equals 0, then G also equals 0. Otherwise, B, A, and D also equals 0. So one of these things has to be true. The fundamental pair, CG, equals 0, or A, B, C, and D are all 0, in which case this whole matrix that we're asking the question about is just all zeros. And in that case, we would be asking a dumb question, okay? Because that would make everything 0, always. So what we find from this, basically, is if we want to say C equals 0, the pair, then G, this pair must equal 0. Because this pair equals 0, G also equals 0. So we know that CG equals 0. That's our new condition, okay? And from that, we can simplify. We have the 4 pairs and 6 equations. But after giving it the condition of CG equals 0, this goes down to 3 pairs and 3 equations. So it just got a whole lot simpler here. And we are left with AF equals BE, AH equals DE, BH equals DF. And then, of course, the pairs AE, BF, and DH. Okay, let's simplify this again. Next thing we're going to say, we're looking at these fundamental pairs. We're going to say BF equals 1. Now, that is a simple thing to say, but it's not. Because really what this means is that B equals 1 over F. Because that just comes from these F's canceling and you being left with B equals 1 over F. Because we know that this is true, we can write this as, we can say that F equals B inverse, which just means 1 over B. Actually, I guess we don't really need the notation, but I just have the notation used a lot. So looking back at our equations, we have AF equals BE, right? But if F equals 1 over B, then this is A times 1 over B equals B times E. And that is the same as to say A equals B squared E, right? So that's a simplification from here. And then we also have the equation, BH equals DF, which becomes BH equals D times 1 over B, which becomes D equals B squared H. Because you just multiply BH times B equals D times 1 over B times B, and then these cancel out, and then these go together and do a nice B squared for you. So then you're left with B squared H equals D. Okay. And then we're left with the equation AH equals D, which is going to be unaffected for now, but we can write this up nicer again. AE is a fundamental pair. DH is a fundamental pair. You know that BF equals 1. We have that D equals B squared H. A equals B squared E. And AH equals D. B. Now we could combine these two equations using the b squared and try to do something with that. It's better not to. I got to be honest with you. I tried it, and that's definitely another option. I don't know. We could do it that way, but that's not the way I did it, because I could explain. You just have to be. You have to be careful about making too many substitutions. It gets a little complicated. Because then you can't substitute that into here again. It just doesn't work. You have to be careful. You have to be careful. You just get that b squared equals a over e equals d over h. Doesn't really tell you anything. You have to make another assumption. And the next assumption we are going to make is that h equals -1. All right, and let's see what happens. So now d equals negative b squared. And we're also now I'm just going to take this, we can kind of reasonably deduce it later, but I'm just going to take the time to say it up front. Saying that e equals 1 does help. So it would also be equivalent to say that h is not -1 and d is -1. That would be an equivalent statement to saying that h is -1. But we're just going to use the fact that h equals -1 and e equals 1. So now we're left with a equals b squared and d equals -b squared. And everybody's going to be like, Adam, okay, what about it? Where are we going with this? What are we doing? And I got to be honest with you guys. All that's left is this h equals d e, and this is just b squared times -1 equals -b squared times 1. And that's just -b squared. So really, we're actually done. If you think about it, we answered everything. And I'm going to go back through it, and we're going to look at it. But we answered the question. We needed to know what a equals, b equals, and h equals. Okay. So taking it from the top, we know that c is 0. Oh, actually, I don't like how I did this. So this was the original question that we started off with, was what would these things have to be equal to? What would these 8 things have to equal for a tensor b to equal b tensor a? Okay. So we figured out that c equals 0 and g equals 0. B equals b, right? B, it's up to you with b. That's the beauty of math. That's why there's still a letter involved. Plug in your favorite number where that letter goes, and it'll still be true. Okay? Continuing. From the fact that bf equals 1, we know that f is still 1 over b. Okay? And then we know that h is -1 and e is 1. And then we know that d is -b squared and a is b squared. And I don't know if you realized it, guys, but we answered our question. Matrix A is b squared, b, 0, -b squared. And matrix B is 1, 1 over b, 0, -1. And what does that mean? Well, AB should equal BA, right? So, all you can do, right, is write it out and find out, okay? So that's what we're going to do, you know what I mean? because we can only find out if we're right by checking. Okay, this is painful to draw at this point, but we're going to do it the other way now. We're going to see that these are all equal. Okay, so now we see how we have unique matrices A and B such that Kronecker product is equal. And notice we still have the fundamental pairs. AE equals B squared. DH equals B squared. CG equals 0. And BF equals 1. It worked out still. So I don't know what the, significance to these fundamental pairs is. And then notice how entries like what? what would AH equal? DE. But you can kind of pick these. AH must be equal to DE, and then where is that pair? DE and AH. Well, that's got to be, we know from the equations that that's that one where it's the negative b squared equals negative b squared. And we see that right in the middle here. Negative b squareds. It all works out in the end. Again, I don't know what the significance of these, of this is, this weird system of matrices that is produced. I can tell you that I would be comfortable. This was, one second, where was it? Because this was the conclusion that I ultimately came to. I would be comfortable. Okay, so this is a little bit more complicated. But if we again take a look at, okay, so this is now, I'm in over my head, if we look at again, b squared, b, 0. This is a little homework for the reader. If you want to try something at home, I would maybe look at this. This is a little bit interesting, and I don't want to work it out. Okay, so if you take these as pairs, v1, v2, if these is columns, v3, v4. I'd be, okay, I don't actually want to talk about that. I would be comfortable with making the conjecture that this tensor product, those just make a column matrix, or those just make column vectors that are the matrix of this tensor product. And what that would say to me is that you need the 4 permutations of the tensor products of 2 linearly independent vectors spans R4. That's how I'm going to end the video for all the real math heads out there who stuck to the end. I don't have a fun, usually I would have a fun outro where I scream to my folks, but my hand hurts from writing, and I don't know. I hope this was a fun video, guys. This is the kind of stuff that I do in my free time, I guess. Fortunately or unfortunately, this is, So I don't know. I hope this was a fun little glimpse into kind of the problem solving stuff that I can get up to sometimes. You know what I mean? The mischief. The behind the scenes mischief over here on Lesh. The ins and outs of the day to day. That's what I'm. But no, I hope you enjoyed that. I hope that this was, accessible to people. I hope people liked I hope everybody could find something in this that they, at least thought was kind of interesting, at least. Maybe walk away thinking math is cooler now than when you did coming into the video, or something like that. Or maybe you think I'm cooler. I don't know. Hopefully you enjoyed this, everybody. Hopefully everybody enjoyed this. All right. That's my opinion. But yeah, thank you guys for watching. I appreciate it, and I'll talk to you all soon. Ladies and gentlemen, thank you for watching. Appreciate you. Love you. Bye.
Dude, what happened? The new video isn't doing good.
I know, it's really bad.
That sucks.